In this problem, we're going to calculate principal strains as well as the corresponding angles at which these principal strains occur. We're also going to calculate maximum in-plane shear strain and the angle at which that occurs as well. So this is very similar to how we calculated principal stresses. Here we're just going to use the strain transformation equations to get our principal strains. And then we'll use the corresponding equation for calculating the angle at which those principal strains occur. So we're given this material element. So in black is the undeformed material element, and in blue is our deformed material element. So you can see there's some amount of strain in the x direction in this material element. You can see that here. We have some epsilon x. There's some strain in the y direction, and we also have strain in the shear. Okay, and we're defining x as positive to the right, y as positive up. So if we were to make some strain measurements, we can say that what we'll use for our strain in this problem, that epsilon x is equal to 120 microstrain, epsilon y is negative 30 microstrain, and gamma xy over 2 is 50 microstrain. Alright, so the first thing we're going to do is calculate what our principal strains are. So to do that, we will use the principal strain equation. And that is epsilon 1 and epsilon 2 is equal to epsilon x plus epsilon y divided by 2 plus or minus. And remember, the plus is for calculating epsilon 1, the minus is calculating epsilon 2. The square root epsilon x minus epsilon y divided by 2 squared plus gamma xy over 2 squared. Okay, so from here, this is just simply plugging everything into a calculator, and we're going to get that epsilon 1 is going to be equal to 142.3 microstrain. And epsilon 2 is equal to 7.73 microstrain. So now we want to know at what angles the planes of these maximum and minimum principal strains occur. And again, this is the same process as principal stress, or a similar equation, I should say. So the principal angles, we're going to use the equation, the tangent of 2 times theta p is equal to gamma xy over epsilon x minus epsilon y. So we'll do some algebra to get that the principal angle theta p is equal to 1/2 times arctan gamma xy over epsilon x minus epsilon y. Okay, so then we plug this into our calculator. We have everything here, gamma xy, we know epsilon x, we know epsilon y. We plug that into a calculator, and we're going to get that theta p is equal to 24.0 degrees. But remember, there's 2 angles that satisfy this arctan. So it's either 24 degrees or it's 114 degrees. And notice that just like with the principal stress angles, principal strain angles are going to be separated by 90 degrees. So there's a 90-degree difference between these two principal strain angles. So we want to know which of these corresponds to which of the principal strains. So what we'll do is we'll plug one of them into our strain transformation equation and see what number that gives us. So if we plug that theta p is equal to 24 degrees, if we plug that into the equation for epsilon x prime, and just a reminder, epsilon x prime is equal to epsilon x plus epsilon y divided by 2 plus epsilon x minus epsilon y divided by 2 cosine 2 theta plus gamma xy over 2 sine 2 theta. Okay, so notice the principal strain is dependent on the angle that we're looking at, the angle of rotation that we're interested in. Or sorry, the transform strain varies with angle, right? The principal strain occurs at a specific angle. So if we plug in the specific angle, 24 degrees, we know that one of the principal strains occurs at that angle. To know which of the principal strains is at 24 degrees, we plug 24 degrees into theta in this equation for epsilon x prime. So epsilon x prime, if we do that at theta equals 24 degrees, so I'm just writing epsilon x prime as a function of theta, theta will be equal to 24 degrees, we're going to get a strain of 142.3 microstrain. And if we scroll back up to the principal strains we calculated, 142.3 microstrain was epsilon 1, so that's our maximum principal strain. So that means if 24 degrees, plugging that theta p equals 24 degrees into the equation for epsilon x prime, that means that the theta p of 24 degrees is theta p1, or in other words, that angle corresponds to the maximum principal strain. And we only have to do that for one of the angles to know that theta p1 is equal to 24 degrees, and that means the other one is theta p2, which is 114 degrees, which would correspond to epsilon 2. So now we'll look into the second half of this problem, which is calculating the maximum in-plane shear stress, or sorry, shear strain, I should say, max in-plane shear strain. So we'll make some space for ourselves. We'll say max in-plane shear strain. So the equation for max in-plane shear strain, gamma max in plane this is in the xy plane, gamma max in plane divided by 2 is equal to the square root of epsilon x minus epsilon y divided by 2 squared plus gamma xy divided by 2 squared. Alright, so we just plug this into our equation. We're going to get that gamma, so plug this into a calculator rather. We have all the values, so I'll skip doing that in the video just since that's a simple thing to do. And we'll get that gamma max in plane divided by 2 is equal to 67.3 times 10 to the minus 6 microstrain. Or sorry, 10 to the minus 6 strain. 67.3 microstrain. Okay, and then the last part of this problem is getting the angles for the max in-plane shear. So max in-plane shear strain angle. Okay, so the equation for this is that tangent of 2 times theta s. Theta s is the angle where the max in-plane shear strain occurs, is equal to minus epsilon x minus epsilon y divided by gamma xy. Okay, so if we do the algebra to solve for theta s, we'll have that theta s is equal to 1/2 times arctan minus epsilon x minus epsilon y over gamma xy. Okay, so what we'll do is plug the numbers we know that were given to us, epsilon x, epsilon y, gamma xy. We'll put that into the calculator and we'll get that theta s is equal to -21 degrees. Okay, and we also know there's a second angle that would satisfy this arctan. It's going to be separated by 90 degrees from this first angle that we found, which means that the second angle would be 69.0 degrees. So we want to know which of these angles corresponds to the max in-plane shear strain. So just like we did before, we're going to plug one of these angles into the equation for the shear strain transformation and see what number we get from using that angle. So let's write out our shear strain transformation equation, which is gamma x prime y prime over 2 is equal to negative epsilon x minus epsilon y over 2 times sine 2 theta plus gamma xy over 2 cosine 2 theta. Okay, so if we plug in, we know what epsilon x is, we know what epsilon y is, we know what gamma xy is. Let's use theta s is equal to -21 degrees and see what we get. So if we plug in -21 degrees, so we're going to evaluate this at theta s equals -21 degrees. We will get 67.3 microstrain. Okay, so, and that lines up with what we calculated up here for max in-plane microstrain being 67.3 times 10 to the minus 6. In reality, if we had plugged in 69.0 degrees, we would have gotten that our microstrain would be -67.3 times 10 to the minus 6. So we know that theta S1 is equal to -21.0 degrees, and theta S2 is equal to 69 degrees.